video I'm going to talk about regression. I want to start by talking about the regression ANOVA table. That's my dog Gladys. Yeah, it's almost time for dinner. That's right, Gladys. I know. Gladys loves regression. It's her favorite. But here we go. So I'm going to draw out a table. I'm going to start by drawing out the source, sums of squares, degrees of freedom, mean squares, and then the F ratio. Okay. So the important thing to know, I know, this is Gladys's favorite part. Our first source that we usually talk about is regression. And that's the actual regression equation. Oh, terrible handwriting, but you might get a sense for that. Regression equation. Our second source here is going to be error. And then we're going to have our total. Now, our sums of squares regression is going to be a sum of squares, just like it always is. And our sums of squares error is going to be a sum of squares, just like it always is. So it's always going to be the sum of something squared. But what is it the sum of? And that's the real trick in understanding regression. If we have a regression made up of a series of points, here represented by red dots, and the regression line is represented by the blue line, then we have several components that we can think of. I'm going to draw an estimation, the green dot here. Let's redo that a little bit. And make it a green dashed line. That's going to be our Y bar. Y-axis, X-axis. And you can think of the blue line as generating your Y hats. And your each Y hat sub I is really just the Y value for a given X. So, for example, we might take a level X here, and it intercepts the Y, or intercepts the line right there, intercepts the Y-axis right there. That's a Y hat estimate. And if this X value had been 10, then we might say this is our Y hat sub 10. So Y hat is just for each value of X, it's an estimate of Y given the line. For our first estimate of error, we can think of the line's distance from the mean for each value of X as being something important to keep track of. So for each red dot here, I can look at the distance from a line of best fit to the mean. Sometimes that distance is not very far. I've made a couple errors here. Let me back up. Okay, so now for each value of X, each red dot, I have a corresponding series of blue dots that represent the distance from the line to the mean. The way we represent this quantitatively in our equation is y hat sub I minus y bar. So that's our sums of squares for regression. Now, we might want to say, what about our error? How do we calculate that? Your sums of squares for error has to do with the distance from an individual point to the line. So each of these points has a known distance to the line. And that distance can be represented in the equation by saying, what is the distance from each y sub I to each y hat sub I? Where each y hat sub I, remember, is the blue value. And if I want to stay true to my color scheme, I can go back here and redraw that y hat sub I. In fact, it might have helped me to do that up here too, so I can redraw that just for posterity. Y hat sub I minus y bar. The sums of squares that I'm still left with, that I haven't done anything with, of course, is my total. So I have a sums of squares for my total too, and that's going to look familiar to you, because the total sums of squares is just going to be each of my individual y sub i's minus y bar. Move this axis label here a little bit so you can see better. This looks a lot like something you've seen before. Variance, anyone? When we take that total sums of squares and we divide by degrees of freedom, we get an estimate of variance. It turns out that we're going to do something similar in this table. We have a degrees of freedom, a mean square, and an F value. It turns out the degrees of freedom for a regression is going to be 1. For our simple regression, linear regression equation is going to be 1. And for our error, it's going to be n minus 2. We can go into why those degrees of freedom work in another little episode here. Our mean squares are just going to be the sums of squares for each source, like sums of squares regression, divided by degrees of freedom. Or in the case of error, it'll be sums of squares error divided by n minus 2. And then our F score is just going to be m, our mean squares regression, divided by our mean squares error. So once again, I had a series of points here. Some were on the line, some were far away from the line. I used this blue line to estimate a simple, like y equals b plus mx type equation with a slope and an intercept. That would be a least squares regression. That would be a regression that minimized the error sums of squares. When I think about how that line is fit, I can think about some of the error in this graph being represented by the distance from the regression to the overall mean, this distance here. I can think about some of the error being associated with the distance from the individual point to the line. And then I can think about the total error in the data set being represented by the distance from the point to the mean. When taken all together and moved into table form, I can represent those with these equations, with the sums of squares equations. The sums of squares are related to each individual little distance measure that I just put here. Sums of squares regression is here. Sums of squares error is here. And sums of squares total was the long line